Hi, today we wrap up our work in Chapter 7. We're going to talk a little bit about linear programming, which really is a application of solving systems of inequalities like you were doing yesterday. Now we're going to wrap some business problems around them. And as you know, people in business operate under boundaries, or constraints is another word for that. Limits on the amount of material that they have available, the desired number of products on the market, all kinds of constraints in business. And there always seems to be something that you either want to get the most out of, the most production for your money, or something you want to get the least of, which might be cost involved, right? So manufacturers, business people often looking to minimize cost while they maximize profit. Linear programming gives them a tool to do this. As we explain this process, we're going to be using this problem. So I'll ask you to take just a couple of seconds and read it, and then we'll go over the highlight. Well, it looks like we're the proud owner of a gift shop, and we want to do some advertising. We have two options. We can print brochures, which would be something like you hand out, a little bit more formal. A brochure is. A flyer is a back-to-back usually, or sometimes even a one-sided paper that has sales stuff on it. So we have our choice of either or both of those. We have some constraints, and we have some information about costs. It will cost us 8 cents to print a brochure, and a flyer only 4 cents. A brochure will take 3 pages of paper, and a flyer takes 2. So we don't want to use up more than 600 pages of paper, so there's a limit for us. And we need to have at least 50 brochures. See, we know what we want here, and we have minimums that we are desiring, and 150 flyers, right? At least 50 brochures and at least 150 flyers. And then the question is, how many of each should you print to minimize the cost? So as we get into the linear programming aspect, I'm going to turn the page, and we're going to go through a procedure as we work our way through this problem. And we're first going to begin by defining variables. And you can see from the graph square that I've set up that I want my x to be the number of brochures that we make, and I want my y to be the number of flyers. So we've defined our variables. The cost function, well, they gave us information on that, and I'm going to write it this way. Cost is equal to, and they told us it was 8 cents for every brochure, and we want to sell, or we want to make X of them, and it was 4 cents for every flyer. Alright, I'm good with that. Now it says to write the constraints as a set of linear inequalities, and we really have 3 things going on. The most pieces of paper that we can use were 600 sheets. So how many did it take to make a brochure? I think it was 3. 3x, that would be 3 pieces for each. So this one's going to be about paper. 3 pieces of paper for each brochure, 2 for each flyer, and we have to use no more than 600 pages, so that has to stay less than or equal to 600. That's our first constraint. Then we had some limits on the numbers of, or quantities of, these things that we wanted. So here comes some about quantity. As far as brochures, we know we want at least 50. So it could be more than 50, but the minimum we need is 50. The flyers, on the other hand, we want at least 150 of those. And here's our system of inequalities. Okay? Our job next is to graph this system and find its corners. We need a y that's bigger than 150. So I have my ruler set right there, I hope. Let's see if we can't sketch in that line. Yeah, there we go. We need 50 in the x direction. So there's that line. And our last line has to connect an x-intercept of 200 and a y-intercept of 300. Alright, I have my 3 lines graphed, and now it says that we should find the vertices. So we have one here, We have one here, and we have one here. Since we want it to be above the 50 line, above the 150 line, and beneath positive y, so we want to be under. This is our feasible region right in here. Okay, let's see. We can find the coordinates of these points pretty easily, I think. The x on this one is 50, since it's on that upright line. And if x is 50 in this line, that makes that part, well, I'm going to just do my scratch work here. 350s are 150. So we subtract 150, that's 450. 2 y's are 450, and half of 450 is 225. So 50, 225 is that boundary point's coordinates. This one has a y of 150. And we know that because it's on the horizontal line, but it's also on the oblique line. So if y is 150, that makes 2 y's 300. 3x equals 300, x must be 100. We're solving a system, although really we're doing the work in our head. 100 and 150 is that point. And the last point is the easiest to get. It's on both the horizontal and vertical line. So that's at 50 and 150. And our job, according to this problem, was to minimize the cost function. You take a quick look at my calc, and you can see that I've done those calculations for us. For each of our points, we have to put its coordinates into the function 8 times the x plus 4 times the y. 225. That should be a 2. Let's see. That one is 1,300 pennies, but that's really $13. 100 and 150 is right here, and you can see substituting those into our cost function, that one comes out to be $14. And the last point, which is probably what many of you were thinking all along, well, of course this has to be the cheapest way. It satisfies the 2 need requirements, and it uses the least paper. That one comes out at $10. So we can do our advertising job here for $10. And to answer the problem, we should write a sentence that says we should make $50 brochures and 150 flyers. Alright, and we've done a linear programming problem. Let's go on, because you just want to talk a little bit about the possibilities that could happen when you're doing this linear programming. It could be possible that you would get a system that's called infeasible. That means there are no points that satisfy every constraint. Or if you think about that in terms of the solution to the system of inequalities, there aren't any points that would be shaded in all directions, right? There are no points that fit every constraint. The second type of case that can happen is an unbounded solution, and that is where there are multiple, infinitely many solutions, because you get something that just keeps growing and growing and growing. Like in our problem, we had the line that went from left to right, and it put a limit to our growth. But in an unbounded system, that polygonal convex set would just keep going forever and ever and ever. There are infinitely many solutions. And in some cases, and you're going to see one of these in the problems we work tomorrow, you'll have a set where there are alternate optimal solutions, it says. That means that more than one point gives you either the least cost or the most profit, whatever it is that you were looking for. More than one point maximizes or minimizes. The cost function. Alright, I just wanted to have you get just a chance to try your logicking here. And I'd love to have you think about this. The graph that we're looking at here, is this infeasible, unbounded, or are there alternate optimal solutions? And I hope that you are thinking there aren't any points that are both blue and red. That means that we have an infeasible system here. There aren't any solutions that satisfy both inequalities. This one, we have points that are both shaded blue and red, but it keeps growing forever and ever. This is our unbounded problem. And as far as what an alternate optimal solutions problem looks like, we'll look at one of those tomorrow. Okay, get out there, try the U-Try, and we'll see you in school.